Hi, everyone. Today we are going to talk about modeling harmonic motion, and this is going to be some applications of trigonometry, which is great because we've been spending a couple of weeks talking about trig, and we haven't really gotten to much in the way of real-world applications, so that's what this section is about. And we're also going to see more real-world applications later in the semester, but let's go ahead and get started with this. So, modeling harmonic motion, it sounds really complicated, but it's not that bad. It's basically trig functions are well suited for modeling periodic behavior. All right, so you know that in math, certain types of functions are well suited for certain types of behavior. You know, if you want to talk about interest, then you probably use exponential functions. If you want to talk about maybe like a projectile, like something goes up in the air and falls back down, you might use a quadratic function. So trig functions are useful for periodic behavior because they are what we call periodic functions. So what kind of real world things would have periodic behavior? I guess the most common first example that we usually talk about in a class like this is a mass suspended from a vibrating spring. So we're going to imagine a spring bouncing up and down, okay? And that's going to be periodic. It kind of goes up and down and up and down and up and down. And that's why trig functions are going to be useful for it, especially something like sine or cosine, because the graphs of sine and cosine go up and down. I actually looked around the room around me to see if I had anything I could use to like demonstrate like a spring. And I really, one of these days, I should buy like a slinky and use that to kind of demonstrate this stuff. But I didn't really have a spring, so we're going to draw a picture instead. We'll draw we're going to try to draw a picture of a moving spring. So how do we draw a moving picture? Well, we can't really draw a moving picture, but we can make a graph. Let's put time on the horizontal axis. And I'll draw a few sort of snapshots in time. And we'll kind of get the sense that this is a spring that's moving up and down. So imagine the spring is sort of hanging from the ceiling, and then there's some kind of mass, like some chunk of metal at the bottom of the spring. So it might go something like this. And I'm going to say this is happening at t equals 0 seconds. So what does 0 seconds mean? It's kind of like we have a stopwatch, and 0 seconds is when we start observing this spring and this little mass attached to the bottom. And then maybe we look at it like 1 second later, and maybe 1 second later, the picture now looks something like this. This is at t equals 1 second. And maybe 1 second after that, it has bounced back down. Spring looks like this again. So this is at t equals 2 seconds. And then 1 second later, we look at it, and the spring and the mass I'm imagining to be like a metal cube, some kind of weight that is causing, maybe we pulled the spring and the mass and then we released. and it bounced up and down and up and down. That's what's happening here. And it's back up at t equals 3 seconds. And the idea is, well, what's happening in between these seconds is the object goes up, goes back down, goes back up, goes back down. It looks like a trig function. It looks like sine or cosine, or some version of sine or cosine. Maybe it's like cosine but flipped vertically, you know, something like that. Maybe it's sine or cosine, maybe it's flipped vertically, maybe it's scaled horizontally or scaled vertically, but it does look like we could use sine or cosine as kind of a basis for this type of motion. All right, so that is kind of the informal example, and now I can give you a more proper definition of what exactly do we mean with this phrase harmonic motion. So, definition: if the equation describing the displacement y of an object at time t is displacement. By the way, displacement just kind of means the location of the object. The location of an object. It could be the height. It depends on the context. You know, in this context, we might call it the height, but displacement is just a word we use that covers all possibilities. All right, so we want to allow for the possibility that it might be based on sine, it might be based on cosine, and it might be a flipped version of one of them, or like a stretched version of one of them. So we're going to say y equals a times sine, and then we're going to have another letter in here, not just t for time, but we're going to have this letter, y equals a times cosine. Let me tell you what this letter is. This thing that looks kind of like a lowercase w is supposed to be a lowercase Greek letter omega. It's going to be a constant, okay? But we tend to use Greek letters for certain things, and we use the Greek letter omega for this. If you want to use a lowercase w, that's fine with me. It looks like a lowercase w when we write it. It's just a little more curved. All right, this sentence hasn't really finished yet. If the equation describing the displacement is this or this, then the object is in what we call simple harmonic motion. In this case, let's talk about a is a constant and omega is a constant, and let's talk about what they mean. So we say that the amplitude, I think that's a word that we've used before in a previous section, the amplitude is the absolute value of a. It's a number out front that sine or cosine is being multiplied by. It could be a number like 2. It could be a number like -3. And it tells us the maximum displacement of the object. You know, how high does this thing bounce or whatever. there's going to be other types of objects that are in harmonic motion besides just springs, but the spring is kind of the canonical example, or just the maybe the main example to keep in mind. All right, next is the period. We've used the word period before. We've said sine and cosine have a period of 2 pi. However, this is not just sine or cosine anymore, right? We can't just say the period is 2 pi because this omega inside is changing things. And the period is going to be 2 pi divided by omega. And this is the time to complete one cycle. And I think earlier we had amplitude and period and in a previous section, but I think that this next word that I use might be brand new for us. The frequency. The frequency of this object in simple harmonic motion is going to be omega over 2 pi. So it's the reciprocal of the period, and it is the number of cycles per unit of time. We didn't really say what time was measured in. Is it measured in seconds? Is it measured in minutes? And the answer is it could be any kind of unit of time. So seconds is probably the most common. Let's get a new sheet of paper. You know, I guess I didn't really say this, but I guess maybe I should just address this now. A and omega have to be non-zero constants, right? If A is 0, then we don't really get any kind of up and down motion. And if omega is 0, well, that's not going to be very interesting, right? 0 times t. And if omega was 0, then we'd be dividing by 0 for the period. So yeah, they're non-zero constants. Let's get a fresh sheet of paper here. So visually, I want to talk about what does this look like, because I drew a quick picture of a spring, but what does y equal a times sine omega t look like? And we could also do something like this for cosine, but let's just focus on one of them for now. The idea is that these are just graph transformations. Of sine. You know, so if we know what sine looks like, and then we remember what does it mean to have a constant out front, what does it mean to have a constant on the inside? So first of all, when we do graph transformations, we often start with a picture of the original function. So I'm going to draw a picture of just sine. A quick sketch. All right, and sine goes up, down. All right, let's say this is a quick picture of y equals sine t. And notice that it has a period of 2 pi, because that is how long it takes before the function would repeat itself, right? This is one period, goes up, comes down, goes back up. And then you would like take this picture and sort of copy and paste it to the right. Get another one. And so on and so on. And you get lots of copies of that. That's what makes it periodic. Let's talk about what happens if there's something in there for A or omega. I guess in this, you could think of A as being 1, and you could think of omega as being 1. But let's say, all right, what if they're not both equal to 1? So how about we suppose y equals sine of 6t, so that omega is 6 in this case. Well, we'll draw a picture of this. But first of all, I want to say that A seems like it's still 1, so I guess the amplitude is still 1. The period, however, has changed. The period is supposed to be 2 pi over omega, which is going to be 2 pi over 6, which simplifies to pi over 3. So now if I try to draw a picture of you know what, maybe we could try to draw a picture with roughly the same scale. That's going to help us to really see what I'm trying to illustrate here. So I'll try to make my pictures roughly the same size, at least the y-axis and the t-axis. So I guess that would mean that pi is about here and 2 pi is about here. So I didn't actually draw the curve yet, but we set up the y-axis and t-axis. Where's pi over 3? Pi over 3, we'll say, is about here. So the period is just this. Period is pi over 3, which means that the original graph of sine that goes, up and down and back up, it needs to do all of that between here and here. The period is now very small. So I'm going to try to draw that. Up, down, up. We've taken the picture and we've squished it, right? A lot. Squish. All right, and then by the time it gets to 2 pi over 3, it needs to do that again. So back up, down, and again. Sometimes these get kind of tricky to draw, but you see where I'm going with this. So let's go another period, another couple of periods. Up, down, up, down, up. Can you imagine this as being like a spring bouncing up and down or something? Maybe you could think of some other applications that this would work for also. What's something else that you might see in real life that looks like this? How about sound waves? How about radio waves? Radio waves have a different frequency, right? You tune into a different frequency. All right, so, and also sound waves, the frequency is kind of the pitch of the sound. We'll do a problem involving sound waves in just a minute. Anyway, that is what y equals sine 6t looks like. So I'll write y equals sine 6t. So the 6, the omega, it wound up changing the graph pretty dramatically, right? So you could say that we go through a lot more periods by the time we get to 2 pi. Instead of just going through one period, we've gone through, I guess, 6 periods by the time we get to 2 pi. I want to show you one more, because what about a? What if a is something other than 1? So suppose y equals, let's do 2 sine pi t. Let's see if we can graph this. So 2 is going to be my a, pi is going to be my omega. So instead of like a integer like 6, pi is omega this time. So what's the period? I think that finding the period is helpful for graphing. You know, I think knowing the period was helpful for these first two graphs. So let's do that here. The period is 2 pi over omega, which in this case is 2 pi over pi, which is 2. Okay. This time when I draw a picture, this one might not be exactly like set up with the same kind of scale as those other ones, but that's okay. By the way, I'm kind of focusing on the positive t direction. The reason why we're using t is because this usually represents time. And I mean, I guess the definition of harmonic motion said that that t represents time. So we're interested in kind of starting at t equals 0 and going forward in time. That's why when I drew this second picture here, I guess I started at 0 and I did not draw an arrow pointing to the left. Maybe I should draw an arrow pointing to the right. Like indicate that this keeps going here. But we're not really going back in time. We're not going before 0. So I'll do the same thing here. I'll start at 0 and only go to the right. What kind of scale should we set up? Because the amplitude is 2, I know that the graph is going to go to a maximum height of 2 instead of just 1. So if this is 1, we need to go up to at least 2 in our picture, like in our scale that we're setting up, right? When you set up the scale, make sure that it goes to at least 2. And what about the horizontal? So I know that the period is 2, and when we draw pictures of trig functions, we like to draw at least 1 period. So I think what I'll do is maybe I'll set up the horizontal and vertical scale to be pretty similar. Like if this was 1, 2, then maybe this is 1, 2. 3, 4. Let's do that. Other than those changes, the overall shape of sine is still going to be the same. It's still going to go up, come back down, go back up. The period now is 2, so by the time it gets from here to here, it needs to have done 1 complete cycle, 1 complete up and down and back up. So we start at the origin, and I guess that means if it's gonna do that, it's gonna touch 2. It's gonna touch 1 also on the way down. So go up and down and up. So we've drawn 1 cycle. Let's go ahead and draw the second cycle. All right, so the amplitude on this one made the graph go to a higher value and a lower value. It's kind of like we took sine and we stretched it vertically because of the 2 out front. So on this page, you know, we drew some pictures, and I guess one of the messages that I want to get across is if you have to draw one of these pictures, or maybe if you're like given a picture and you have to identify what is the period or what is the amplitude or things like that. One thing I want you to understand is that in drawing these pictures, I know the overall shape of sine. And the overall shape of sine is not really changing. You could say that all 3 of these pictures are similar in a sense. They all kind of have that waving up and waving down kind of shape. What makes these pictures really different is the horizontal scale and the vertical scale. You know, and setting up the scale carefully is what helped us get these pictures. Like that's what we did here. We figured out what the period is. We figured out it needed to do a period by the time it got there. Figured out what this period is. It needs to do a complete cycle by the time it gets there. All right, so setting up the t-axis and the y-axis accurately is very important. One more thing. What about what about frequency? Like we talked about amplitude, we talked about period. What about frequency? So, how about for this one, I find the frequency. So the frequency is omega over 2 pi, the reciprocal of period. So pi over 2 pi. So this is 1 over 2. Frequency is 1 over 2. What does the 1/2 represent? Well, on the previous page, when we had the definition of amplitude, period, and frequency, we said that the frequency equals the number of cycles per unit of time. So maybe if we imagine that t is in seconds or something like that, how many cycles have we completed by the time we go from 0 to 1? Like 1 unit of time has passed. When 1 unit of time has passed, we've completed half of a cycle. Right? We went up and down. That's it. That's half of a period, right? So the frequency is 1/2. We've completed half of a cycle by the time we got to 1 unit of time. The next 1 unit of time also does half a cycle, and the next 1 unit of time also does half a cycle, and so on. So that's what frequency means. All right, let's look at a word problem. Let's look at an actual type of problem you might see. So let's move this up. So what we just did was just kind of a discussion of graphing these, but let's look at a word problem. So example, and this one is going to be about, instead of talking about a spring and a mass attached to a vibrating spring, let's talk about a musical instrument. So standard tuning for a 4-string bass guitar looks like it's 4 strings. I'm not going to quiz you on like how to tune, a guitar or anything like that, but the notes G, D, A, E are the 4 strings. And when a string is played, the air vibrates. So we said earlier that trig functions are well suited for modeling periodic behavior, and the first example we gave was a vibrating spring, and that was a spring, not a string. And now we're talking about a vibrating string. So, basically you pluck a string on a bass guitar, and the string is going to vibrate up and down, and that causes the air around it to vibrate, and that's what we call sound waves. And the vibrating air reaches our ears, and we perceive the note according to what note was played. Here, I'll tell you what, I can actually show you this because I happen to have bass guitar. I'll tell you that I do this word problem in pre-calculus every semester, but this is the first time that I've done this lesson from home where I actually have a 4-string bass guitar. So, what did we say? G, D, A, E. So let's play A, the A string, okay? What I want you to see is just, what I was talking about, that the string is going to vibrate. I don't know how well you can hear it over the mic. It's not plugged in, but Let me get closer to the mic. So it's this string. What I want you to see is that this string is vibrating, right? And it vibrates very quickly. But if we were to maybe like record a slow motion video of this or something, maybe you'd be able to see how the string is moving according to something that looks like a sine or a cosine function, you know, up and down and up and down, but it's doing it in a smooth periodic way. We can get back to the actual problem right now, but yeah, basically, I think the textbook has an example about a tuba, and you could also look at that in the recommended textbook. Example 2 is about a tuba, and a while back I adapted the problem to be about bass guitar, and you know, the string vibrates the air that reaches our ears, or in this case it reaches a microphone, and we perceive that as sound waves. So let's get back to the problem, because I haven't actually asked the question yet. Okay, so I haven't actually asked you a question yet. So what's the question here? There's going to be a few parts to it. First of all, we're going to be given a function, and it's going to tell us that the variation in air pressure, like you might say, what does it mean to say that the air vibrates? Like, how do we measure vibrating air? Well, it's actually that the air pressure varies when the note A is played, is given by. So this is going to be a long word problem, but it's going to give us a function to work with, and it's v of t, and it equals 0.2 sine 110 pi t, where t is in seconds. And then in parentheses, I'm going to tell you that, you know, I'm not going to test you on this, but v is in pounds per square inch. All right, so this is a math class. This is not like a physics class. We don't really talk about variation in air pressure very much, but just for this problem, in case anyone was wondering, V is measured in pounds per square inch. All right, what's more important to us is just knowing that this is in seconds and this is the formula. So now I can ask us some questions about this. And part A is going to be find the amplitude, period, and frequency. We should be able to do that based on what we've said so far. Part B, I'm going to say sketch the graph of V of t. We should be able to do that based on the discussion we had about what the graphs look like. I'm going to ask you to try these, but I have 2 more questions. If the note is played louder, how does the equation change? And one more part. If the bass guitar is out of tune, which my bass guitar might be out of tune, how does the equation change? So 4 parts. I'd like you to take a minute and think about this. Pause the video if you'd like and work on this for a minute, and then I'll talk about it. All right, so let's move this up. So everything we do for this problem is going to be based on that formula that was given to us. And you might see some word problems like this in this class where for harmonic motion, where we give you the function and then ask you some questions about it. So part A, amplitude. The amplitude in this case is simply the absolute value of 0.2. It's the number that was out front, and that simplifies to just 0.2. That's all. It's just the constant out front. The period for this problem, it's supposed to be 2 pi over omega. So what is omega in this problem? Is it 110? Is it pi? It's actually both. It's 110 pi. So we need to make sure that omega is 110 pi, because that is the constant in front of t. Okay, so let's simplify this. Well, pi over pi cancels and just gives us 1. What's 2 over 110? This is going to simplify to 1 over 55. Okay. And the frequency. The frequency is omega over 2 pi, which is 110 pi over 2 pi. Do you see that once you find the period, it's actually very quick to find the frequency, and vice versa, because they're just reciprocals of each other? This is going to be 55. So we're done with part A, but I just want to say one thing before we move on. Frequency is cycles per second. I mean, really, we said that the frequency is the number of cycles per unit of time, and this problem said that time is measured in seconds. So this vibrating guitar string is doing 55 complete up and down cycles per second. That's why I was saying we would need to record like a slow motion video in order to really see it. 55 cycles per second. I want to tell you that this is sometimes written as hertz or just Hz. Okay. And so I'm going to tell you that the pitch of a sound, like how high or low pitched it is often measured in hertz. 55 hertz is what we call the note A. If something is making the air vibrate in your ears at makes your eardrum pick up the vibrating air vibrating 55 times per second, we call that the note A. I'm going to put that all in parentheses. That's all kind of a side note. Let's do part B right here. So we want to draw it, and you could imagine maybe t equals 0 is when the string is plucked. So we don't need to go in the negative t direction. We're just going to go in the positive t direction. Notice that we already found the amplitude and the period. That's going to help us graph this, because I know that the highest that this picture needs to go is a height of 0.2. And the lowest that it's going to go is a height of negative 0.2. I also know that it's going to complete one period by the time it gets to 1 over 55. So let's put 1 over 55 here. Let's just make this our scale. Let's say that's 1 over 55. And let's say this is the halfway mark. And now I can draw what looks like an ordinary sine curve, but what's important is that we set up the scale on the t-axis and I guess this would be the v-axis, or v of t. We set up the scale correctly. So we go up, down, up. You should draw at least one period, but you could draw more if you want. And then finish it with an arrow to indicate that it keeps going. Right? All right, so that's a good enough graph. Let's do parts C and D. You know, if we were doing this in person, I usually like to ask people for, you know, what do they think for part C and D? Because part C and D it's kind of asking you for an answer in your own words, right? The answer to part C and D is not a number. The answer is just like a sentence. So part C said, if the note is played louder, how does the equation change? So I'm going to just explain this in words. I'm going to say louder would be a bigger amplitude. So why do I know that? Why do I know it's a bigger amplitude? Because, you know, our perception of things being louder would be that the air is vibrating more strongly, which means the string is probably vibrating more strongly, and the amplitude's going to be larger for that reason. So 0.2 would be replaced with a larger number. That's all. That's all for part C. Something like that. Maybe it would be 0.3. That would be the same note, but louder. And part D, what if the bass guitar is out of tune? How does the equation change? Well, the wrong pitch would be played. When something's out of tune, we say that, you know, you're trying to play the note A, but what you're actually playing is, it's kind of off a little bit. So instead of the frequency being 55, you'd have something that's a little bit off. Instead of the period being 1 over 55, it would be a little bit off. So wrong pitch equals wrong frequency. So omega would be a different number. That's all I was looking for part C and D. What number would it be? Well, we don't know. It depends how out of pitch, you know, it depends how out of tune the bass guitar is. You know, maybe instead of 110 pi, maybe it would be like 105 pi. You know, and that would be considered out of tune, and it would sound approximately like the note that it's supposed to sound like, but it would be a little bit off. Maybe 115 pi, something like that. All right, I just moved the page up, and we've got one more thing to talk about. As we've been talking about harmonic motion, you might have noticed that in the definition, it said simple harmonic motion, and that seems to suggest that maybe there's some other type of harmonic motion that's not so simple. Whenever we are trying to model things in math, what does modeling mean? It means that we're trying to use like equations to simulate real life phenomena. And what winds up happening is simple equations are easy to work with, but they don't always get everything exactly right. And if you want to be more realistic, then the formula has to be a little bit more complicated. So it's a trade-off. Do you want formulas that are easy to work with, or do you want formulas that are accurate? And in mathematical modeling, we usually meet somewhere in the middle. We want things that are relatively easy to work with and relatively accurate. So what would you say? I know that this is a pre-recorded video, but think to yourself, what would you say is not realistic about the example we just did? I'll tell you. So the string vibrates up and down forever. Does it really vibrate up and down forever, though? In real life, if I play the guitar string, you hear it for a few seconds and then it fades out. So it doesn't really play forever. And that's what we want to address here. That the same thing could be thought of about a vibrating spring. The spring is not really going to vibrate forever. It's going to vibrate for a while, and then it's going to kind of settle down into some kind of equilibrium. So, to make this whole thing more realistic, if we multiply y equals a times sine omega t by, we're going to multiply it by something to make it more realistic. So I said that it's going to have the effect of making the equation more complicated. If we multiply it by e to the negative ct for some c greater than 0, then y gets smaller. I'm going to put y in absolute value bars, actually. Y gets smaller over time because e to the negative ct gets smaller over time. So this is a trick to make our formula for harmonic motion more realistic. And we have a term for this. It's not going to be simple harmonic motion anymore. Definition: if the equation describing the displacement y of an object at time t is y equals k e to the negative ct sine omega t, or y equals k e to the negative ct cosine omega t. Gonna say for c greater than 0, then the object is in damped harmonic motion. Damped harmonic motion. And this is often going to be more realistic than simple harmonic motion. But as you can see, the formula has gotten a little bit more complicated as a trade-off. Let me tell you what these letters represent. K is the initial displacement. Okay, so this is also allowing for an initial displacement, and then c is called the damping constant. Basically, these constants are just going to vary from one problem to the next. 2 pi over omega is still the period. Now, what is the amplitude? Well, the amplitude could be thought of as changing over time. So let me draw a picture here that might help clear this up. First of all, I'm going to draw two pictures, in fact. All right, first picture is going to be simple harmonic motion. Second picture is going to be damped harmonic motion. And it's just going to be one example of each. And simple harmonic motion, I'm going to use A times sine omega t. And we'll draw just some kind of example like that. I guess the maximum height that we go to is the absolute value of A, and the lowest height is negative of that. What winds up happening for damped harmonic motion is a little bit harder to draw. Let's see if I can do it. All right, can you see what I'm trying to do there? If we imagine this as being like a sound, maybe it starts off pretty loud and then it fades out over time, goes almost to zero. Now, sometimes when we draw these pictures, this is the t-axis, by the way. Sometimes when we draw these pictures, k e to the negative ct sine omega t. Sometimes I might draw a little dotted line. Now, I want to be clear, the dotted line that I'm about to draw is not an asymptote. Technically, it is not an asymptote, but I'm going to draw a dashed line here. I know we sometimes use dashed lines to represent asymptotes, but I'm using a dashed line just to kind of show how the wave is contained. It goes up to here, down to here, up to here, down to here, and it stays between those two. In this case, for damped harmonic motion, the dashed line would have to be a curve. Again, this is technically not an asymptote, although it might feel like one. Let's see. All right, so the idea is that the wave is contained between those two curved lines. In fact, these dotted lines are the function y equals k e to the negative ct and y equals negative k e to the negative ct. Those are the equations of those two curves. So if they look kind of exponential in a way, that's why. So what's the amplitude of damped harmonic motion? Like, simple harmonic motion, we have this thing called A, and we could say that the amplitude is a constant. And that's why it goes up and down, and it's always going to the same height. It's always coming down to the same lowest value. For damped harmonic motion, what's the number out front? The number out front is this whole thing. Instead of just A, we have this whole thing out front. And this determines the amplitude at time t. So the amplitude is changing over time. It starts off loud and gets quieter and quieter as time passes. So, maybe if we talked about the bass guitar string being plucked, maybe this would make it more accurate if we turned the problem into a damped harmonic motion problem. But what I'd like to do is I'd like to do a different word problem. Let's get away from the whole bass guitar thing because we spent a lot of time on that. I want you to see another real life application of harmonic motion. So we'll get a fresh sheet of paper and we'll do a problem involving this type of harmonic motion. All right, so give me a minute or so to write this problem. Some of these word problems seem pretty long. All right, instead of talking about a musical instrument and instead of talking about a spring with a mass attached to it, let's talk about something else. We're going to talk about a stone dropped in a pond causes waves to form. Earlier I think I used the word wave, and I want you to understand that trig functions, especially in the sense of harmonic motion, they are good for modeling springs. They are good for modeling anything that vibrates. They're good for modeling radio waves, sound waves, and water waves. Just literal waves of water. It's also good for one type of thing that I don't think we're going to cover today, but a pendulum swinging back and forth. That would be another example. All right, the up and down motion of the water at a point is modeled by y equals k e to the negative ct sine omega t. And I guess I should address that a lot of the examples that I've been doing have been with sine, but you could see some word problems that use cosine instead. It's not really that different. At some time, the amplitude of the wave is measured. And 20 seconds later, it is found that the amplitude has dropped to 1/10 of this value. Find the damping constant C. And I think I'll do this one for us. This is a different kind of problem. All right, so this doesn't give us the constants K and C and omega. In fact, it's asking us to find one of them. But it did give us some information. There's something about 20 seconds. There's something about 1/10. So here's what we'll do. We'll say that the amplitude at time t is ke to the negative ct. All right? I said that on the previous page, that that expression determines the amplitude at time t. "20 seconds later, it is, instead of ke to the negative ct, it would be ke to the negative ct plus 20, because that's 20 seconds later. All right, I want to take this sentence from the word problem and turn it into an equation. The amplitude 20 seconds later is supposed to be 1/10 of the amplitude originally. So this is supposed to be 1/10 of this. So I'm going to do that. This is 1/10 of this. From this, we want to find C. Let's keep in mind, what's our goal? It says find the damping constant C, so that's what we want to find. First thing I notice right away is that the K's cancel out. K and K, you could cross them out if you want. So we'll get rid of the K's. And while I'm at it, I'm going to distribute this stuff that's in the parentheses, like negative C times parentheses. Let's distribute. Let's make it negative CT minus 20C. And on the other side, all I'm doing is getting rid of the K. Okay. That's good, because if we are truly going to, if we're really going to find the damping constant C, we needed to get rid of K, and hopefully, like, there might be some way that we can cancel out T. Maybe not right now, but maybe a little bit later we can get T out of this and just truly solve for C as a number. Otherwise, we'll solve for C in terms of the other constants if we have to. All right. Maybe what I just said out loud is going to kind of help us. I said I would like to be able to cancel the t's out, and that helps me notice that e to the negative ct minus 20c, that we could write this left-hand side like this. I used a little property of exponents that says, you know, if you have an expression up in an exponent that has something minus something or something plus something, either way, you can split it up. E to the this, e to this. Of course, the great thing about doing that is we can cancel this piece and this piece. It's the same thing on both sides. So I'm really happy about that, because now, look at this. There's no, we canceled K out at the beginning of the problem, and now there's no T in the problem either. So we simply have an equation with one unknown, and it's the unknown that we're trying to solve for. So it's working out really well. E to the negative 20c equals 1/10. That would be considered an exponential equation, and we talked about exponential equations earlier in the semester. So what do we want to do here? We could do ln of both sides. Negative 20c equals ln 1/10. How about that? That's going to help us find c. So we could say that c equals negative 1 over 20 ln 1/10. Should we leave it like that? Yeah, I think it's okay to leave it like that. That is the damping constant C. And, I would leave the answer like that. Just put a box around it and say we're done. That's good. I'm going to tell you that I found on a calculator that this is approximately equal to 0.12. All right, so that's the damping constant here. This problem was about a stone being dropped in a pond. It caused water ripples. The water waves um, dissipate over time, right? The water goes up and down and up and down, but then it kind of settles over time. And after 20 seconds has passed, the amplitude has dramatically reduced to only 1/10 of what it was. And yeah, we have a damping constant. I guess you could imagine that if you were to do the same thing, but instead of dropping a stone into a pond of water, if you dropped a stone into a pond of mud, maybe you'd get, you know, maybe you'd still get some waves depending on how thick the mud is, right? So the damping constant and maybe the constant K, those are going to be affected by like what kind of substance you're working with. Maybe mud is not the best example. Maybe like oil. If you dropped an object into a puddle of oil, it might ripple differently than water. By the way, another way to write this, this is equivalent to, you could also get the answer to look like positive 1 over 20 ln 10. Can you see that that is equivalent to what we got? Why is that equivalent to what we got? Well, yeah, it makes sense because if you look at what we got and you say there's a negative, like a -1, there's a rule about logarithms that says that the negative could be brought inside as an exponent, and 1/10 to the -1 is 10. So you kind of bring the negative inside and it flips the 1/10 into a 10. But I'm okay with either one of these. Either one of these answers looks fine to me. One last thing. One last thing. All right, so far we've done simple harmonic motion and damped harmonic motion. We can also do shifted harmonic motion. Shifted like y equals a times sine omega t minus c plus b, or y equals a times cosine parentheses omega t minus c plus b. So what's happening? What is the c and b now? The c and the b are shifting the graph horizontally and vertically. The b is probably the easiest one to deal with, because plus b, if b is a positive number, it just means you take the graph and shift it up, right? You have a graph plus constant, y gets moved up. Same thing over here. If b is negative, like if you had one of these minus a number, then you're shifting down. So shifted harmonic motion. An example that I've seen in the book, example 4 in the book, and I'm not going to work through this whole thing. I'm mostly interested in the two types that we talked about, simple harmonic motion and damped harmonic motion. I just am doing a very brief little discussion here that shifted harmonic motion also exists. And it is useful for some other types of applications. So there's one about astronomy. It says the star Delta Cephei. Actually, I'm not sure how to pronounce that. Um, I think that constellation is a whale, and that Delta is the, well, anyway. I'm a little rusty on my astronomy, but I used to know some of those things. All right. This star varies in brightness according to. So it's a variable star. There are stars in astronomy that don't just have the same constant brightness, that they vary, and it actually varies according to a shifted harmonic motion using cosine. That's pretty cool. So the +4. So what does this mean? What does this mean? I'm going to say that this means, I'm going to fit this here at the bottom of the page. Even without graphing this, what could we say about this +4 and the amplitude? Maybe I could imagine the graph without the +4. Like pretend the +4 wasn't there. We could graph this. And then the +4 means you would take the whole graph and shift it up, right? So if the +4 were not there, then I would say the amplitude is 0.35. The highest that this is going to go is a brightness of 0.35, and the lowest it's going to go is -0.35. But because there's a +4, take all those numbers and add 4 to them. Okay, so this means the average brightness is 4, and it oscillates. Oscillates is a good word for something that has this kind of periodic back and forth behavior. It oscillates between, what's the lowest that it's going to go? -0.35 plus 4 is 3.65. And what's the highest it's going to go? 4.35. Let me give you a chance to see all that. So I'm not really asking you a question right here. I just thought that I would acknowledge, shifted harmonic motion, and it does have real life applications. And, I guess today we talked about a mass suspended from a spring. We talked about a bass guitar string being plucked. We talked about a stone being dropped in a pond. Now I'm telling you that the brightness of a variable star can also be measured with harmonic motion, and that there are also other applications, such as a pendulum swinging back and forth, or maybe something involving radio waves. So lots of applications involving sine and cosine. All right, so there are lots of applications involving sine or cosine, or maybe, some graph transformation version of sine or cosine. And we saw some of them today. I'd like to tell you that, in math, every word problem is different. So we saw a couple of problems today, but you might see some problems that are different. So they don't always fit into like a nice template. You just have to be careful with word problems, read them twice, be very careful about what is given and what is it asking you for. The other thing that I wanted to say is that a little bit later in the semester, we're going to see some other applications of trigonometry, sine and cosine, and maybe some of the other ones too. And those applications that we're going to see later are going to be different. They're going to involve triangles and just angles in general. Triangles, angles, shapes, distances. But the ones that we talked about today, the applications today, are mostly just about things that are waving up and down or waving back and forth. And that's what harmonic motion is all about. Okay? So that's it. And I hope everybody is having a good one, and take care. I'll see you soon.